In this lecture, we show how to implement two iterative methods for finding the approximate solution to a system of linear equations, assuming that the system of linear equations has a unique solution. The iterative methods that we will present here are the Jacobi or Jacobi method and the Gauss Seidel method. We illustrate these two methods using the following system of equations. The two methods start out the same way, by solving for a variable in terms of the other variables in one equation. For example, we can solve for x sub 1 in the first equation to get x sub 1 equals 6 minus 4 x sub 2 minus x sub 3. Then we can solve for x sub 2 in the second equation to get x2 equals minus 4x1 minus x4. We can solve for x sub 3 in the third equation to get x sub 3 equals 11 over 4 minus x2 over 4 minus x4 divided by 4. And we solve for x4 in the fourth equation to get x4 equals minus x1 divided by 4 minus x3 divided by 4. We end up with an equivalent system of equations where each variable has an equation expressing it in terms of the other variables. We can treat this equivalent system of equations like a recursion for the two methods. We first demonstrate the Jacobi method with 3 iterations. We begin by guessing at the exact solution. Although any guess is as good as any, let's have x1, x2, x3, and x4 each start at 0. For the first iteration, we plug our initial guess into the new system of equations. All the terms involving variables on the right side of each equation are 0, so that the new x1 is 6, x2 will still be 0, x3 will be 11 over 4 or 2.75, and x4 will still be 0. We now use these values to get the next set of estimates for iteration 2. The new value of x sub 1 is 6 minus 4 times x2, x2 is 0, minus x3, x3 is 2.75, so that x sub 1 becomes 3.25. The new value of x2 is minus 4 times x sub 1. X sub 1 is 6, minus x sub 4 is 0, giving us minus 24 for the new x sub 2. The new value of x sub 3 is 11 over 4, minus x sub 2 divided by 4, x sub 2 is 0, minus x4 divided by 4, x4 is 0, giving us 2.75. The new value of x4 is minus x1 divided by 4. x1 is 6. Minus x3 divided by 4. The old x3 is 2.75, giving us minus 2.1875. For iteration 3, we plug in these values. We leave it as an exercise for the viewer to check that these will be the calculations and the updated values of x1, x2, x3, and x sub 4. Using the same transformed set of equations and the same initial guess for x1, x2, x3, and x4, we now demonstrate the Gauss Seidel method. With all the starting values being equal to 0, the new x1 is 6. And here is where the two methods diverge from each other. The new value of x2 is minus 4 times x1, but this time we use the most recent value that we had obtained for x1, and this is 6. So we have minus 4 times 6, minus x4, which is 0. So x2 is now minus 24. The new value of x3 is 11 over 4. Minus x2 divided by 4. x2 is now minus 24. Minus x4 divided by 4. x4 is currently 0. giving us 8.75 for x sub 3. The new value of x4 is minus x1 divided by 4. x1 is again 6. Minus x3 divided by 4. x3 is now 8.75, giving us minus 3.6875. For iteration 2, x1 becomes 6. Minus 4 times x2, x2 is now minus 24. Minus x3, which is now 8.75, giving us 93.25. x2 will be minus 4 times x sub 1. x sub 1 is now 93.25. Minus x4, which is now minus 3.6875. So that x2 becomes minus 369.313. x3 becomes 11 over 4 or 2.75. Minus x2 divided by 4. x2 is now minus 369.313. Minus x4 divided by 4. x4 is now minus 3.6875, giving us 96.0001. x sub 4 is minus x1 divided by 4. x sub 1 is currently 93.25. Minus x3 divided by 4. x3 is now 96.0001. So that x3 becomes minus 47.3125. For iteration 3, x1 will become 6. Minus 4 times x sub 2. x sub 2 is minus 369.313. Minus x3. x3 is 96.0001. So that x sub 1 will be 1387.25. X sub 2 will be minus 4 times x sub 1, or 4 times 1387.25, minus x4. X sub 4 is minus 47.3125. So that x sub 2 will be minus 5501.69. X sub 3 will be 11 over 4 or 2.75. Minus x sub 2 divided by 4. X sub 2 is now minus 5501.69. Minus x sub 4 over 4. X sub 4 is minus 47.3125. So that x sub 3 will be 1390. X sub 4 will be minus x sub 1 divided by 4. X sub 1 is now 1387.25. Minus x3 divided by 4. x3 is now 1390. So that x sub 4 will be minus 694.313. With this set of equations, the Jacobi method and the Gauss Seidel method will likely not lead to convergence to the exact solution. We examined the original system of equations. Specifically, we turn our attention to these terms. The absolute value of the coefficient of x sub 2 in equation 1 is greater than the sum of the absolute values of the other coefficients. 4 is greater than 1 plus 1 plus 0. The same is true for the coefficient of x sub 1 in the second equation, the coefficient of x sub 3 in equation 3, and the coefficient of x sub 4 in equation 4. Switching equations 1 and 2, we get this strictly diagonally dominant system of equations. Solving for x sub 1 in the first equation, we get x sub 1 equals minus x sub 2 divided by 4 minus x sub 4 divided by 4. From the second equation, x sub 2 is 6 over 4 minus x sub 1 divided by 4 minus x sub 3 divided by 4. From the third equation, x sub 3 is 11 over 4 minus x sub 2 divided by 4 minus x sub 4 divided by 4. And from the fourth equation, x4 is minus x sub 1 divided by 4 minus x3 divided by 4. The viewer can verify as an exercise that these are the calculations and the values one obtains when plugging zeros into all the variables for iteration 1 using the Jacobi method. When plugging in these values, these are the calculations and the new values that we get for iteration 2. And finally, plugging in these values, we get these calculations and values for iteration 3. Now, for the Gauss Seidel method, remember that we plug in the latest value of each variable. These are the results for iteration 1. These are the results for iteration 2. And these are the results for iteration 3. Since we started out with a strictly diagonally dominant set of equations, both the Jacobi method and the Gauss Seidel method should result in convergence to the exact solution. The exact solution, by the way, is given by this set of values. Or up to 6 significant digits, this is the exact solution.